Imagine you're playing pool. You hit the cue ball. It strikes the red ball. The red ball hits the yellow one, and you can predict exactly where each ball will end up. Now imagine you add just one more ball. Just one. Suddenly, everything you thought you knew about predicting the future collapses. You can no longer tell where the balls will be in 10 seconds, in 5 seconds. Sometimes, not even in 2 seconds. And it's not because you're not smart enough, or because you don't have powerful enough computers. It's because the universe simply doesn't allow it. This is the disturbing lesson of the three-body problem. And Richard Feynman spent years of his life trying to make people understand what this really means. It's not just mathematics. It's not just theoretical physics. It's a truth about reality that completely changes how you see the world, the future, and even free will. You grew up believing the universe works like a giant clock, that if you knew the position and velocity of everything now, you could calculate everything in the future. Newton promised this. Laplace swore by it. Classical science built empires on top of that promise. But the three-body problem exposes a crack in that foundation. And when Feynman looked inside that crack, he saw something most people prefer not to see. Chaos is not an exception. It's the rule. And this shouldn't make you comfortable. It should disturb you deeply, because it means there are fundamental limits to what we can know about the future, no matter how advanced our technology becomes. The universe doesn't care about your need for certainty. It doesn't care about your equations or your supercomputers. It operates on principles that make long-term prediction fundamentally impossible. Not practically difficult, but theoretically impossible. And Feynman believed this was one of the most important lessons science had to teach, because it destroys the illusion of total control that humanity has been clinging to since the Enlightenment. Why is something as simple as 3 objects orbiting each other impossible to solve? 2 pool balls, you solve it. 2 planets orbiting, you solve it. Earth and Moon? Solved centuries ago. But add a 3rd planet, a 3rd star, a 3rd celestial body, and suddenly all the equations that worked perfectly transform into a nightmare. And here's what they told you in school, but didn't really explain. It's not that the math gets harder. It's that it becomes fundamentally impossible. There is no general solution. There never will be. It's not a matter of time or faster computers. It's an absolute mathematical impossibility. Feynman used to ask his students, "Do you think the three-body problem is difficult because we're stupid or because the universe is complicated?" And the answer always disturbed people. It's because the universe is inherently unpredictable at scales beyond 2 interacting objects. You can have all the laws of physics. You can have the exact equation governing gravity. You can know with infinite precision where each body is now and how fast it's moving. And still, you cannot predict where they'll be in the distant future. Why? Because tiny differences in initial conditions, differences so minuscule you can't even measure them, grow exponentially until they completely dominate the system's behavior. This is the essence of deterministic chaos, and it destroys the worldview that Newton and his followers sold us for 300 years. This is not a bug in our understanding. This is a feature of reality itself. And once you truly grasp this, you can never look at the world the same way again. Every system with 3 or more strongly coupled degrees of freedom carries within it the seeds of unpredictability. Your weather, your economy, your body, the solar system, all of them dancing on the edge of chaos, and we're only now beginning to understand what that means. The story of the three-body problem begins in 1687, when Isaac Newton published the Principia Mathematica. There was the law of universal gravitation, elegant and powerful. It explained why the moon orbits Earth, why Earth orbits the sun, why apples fall from trees. Newton had cracked the code of the cosmos, or so it seemed. He managed to solve the two-body problem perfectly. Given the mass of two objects and their initial positions and velocities, you can calculate their orbits forever. The mathematics is clean. The orbits are perfect ellipses or hyperbolas, depending on the energy. Everything predictable, everything deterministic. So Newton, being Newton, wanted to go further. What if we had three bodies? The Sun, Earth, and Moon, for example. Or the Sun, Jupiter, and Saturn. He tried to solve it, and tried again, and he couldn't. This bothered him for the rest of his life. In his private letters, Newton admitted that the three-body problem made his head hurt. He came close to an approximate solution for specific cases, but a general solution? Impossible. He died without solving it. And it wasn't because Newton was incompetent. It was because the problem is genuinely insoluble. Decades passed. Leonhard Euler, one of the greatest mathematicians of all time, attacked the problem. He managed to find solutions for very specific cases, special configurations where the three bodies always remain aligned or form perfect triangles. But these cases are so rare, so artificial, that they don't help at all in understanding real systems. These are like finding a pencil balanced perfectly on its point. Theoretically possible, practically irrelevant. Joseph Louis Lagrange entered the fray in 1772. He discovered 5 special points, today called Lagrange points, where a small third body can orbit stably relative to 2 larger bodies. These points are super important today, where we place satellites and space telescopes, but this still wasn't a general solution. It was just another special case, islands of stability in an ocean of chaos. The problem became so famous that in 1885, King Oscar II of Sweden offered a prize to whoever could solve it. The French mathematician Henri Poincaré submitted a work, won the prize, and then discovered he had made an error. When he tried to correct the error, he discovered something far more disturbing than he expected. Poincaré realized that the behavior of 3 gravitationally interacting bodies was absurdly sensitive to initial conditions. Change the position of one of the bodies by an infinitesimal amount, smaller than you can measure, and after some time, the orbits become completely different. Not a little bit different, totally different. Trajectories that started almost identically would diverge exponentially. Poincaré described this as, if we knew exactly the laws of nature and the situation of the universe at the initial instant, we could predict exactly the situation of that same universe at a subsequent instant. But even if the natural laws had no longer any secret for us, we could still only know the initial situation approximately. If that enabled us to predict the subsequent situation with the same approximation, that is all we require, and we should say that the phenomenon had been predicted. But it is not always so. It may happen that small differences in the initial conditions produce very great ones in the final phenomena. A small error in the former will produce an enormous error in the latter. Prediction becomes impossible. This was the birth of chaos theory, though nobody called it that for another 70 years. And here's what's truly disturbing. Poincaré discovered this in 1890, but nobody really paid attention. The scientific community ignored it. Why? Because accepting that simple systems like 3 planets are unpredictable destroyed the deterministic worldview that dominated physics. Laplace had said, decades earlier, that an intellect sufficiently powerful that knew all the forces of nature and the positions of all objects could predict the entire future. This intellect became known as Laplace's demon. It was the ultimate promise of science. Total knowledge leads to total prediction. A universe of perfect clockwork, where everything that will ever happen is already determined by what is happening now. But Poincaré was saying that even an infinite intellect couldn't predict chaotic systems, because you can never measure initial conditions with infinite precision. There's always uncertainty, however small. And in chaotic systems, that uncertainty grows exponentially. The future becomes fundamentally inaccessible, not through ignorance, but through an intrinsic property of mathematics and nature. This was a knife in the heart of scientific determinism, but the wound took a century to be recognized. Scientists wanted to believe in the clockwork universe. They wanted to believe that perfect knowledge was possible. So they ignored Poincaré's warning and continued building their deterministic models until computers finally forced them to confront the truth. And that's where Feynman enters the story, because he was one of the first to truly understand what Poincaré had discovered and to explain it in a way that made people feel the full weight of its implications. Drop your comment now and tell me, do you think the universe is fundamentally predictable or fundamentally chaotic? Because this question isn't just philosophical, it completely changes how you see free will, destiny, and even science itself. And while you think about that, I want you to realize something. Poincaré discovered this in 1890, but nobody really paid attention. The scientific community ignored it. Why? Because accepting that simple systems like three planets are unpredictable destroyed the deterministic worldview that dominated physics. Scientists had spent centuries building mathematical physics on the foundation that the universe was a perfect machine. Every effect has a cause. Every cause produces a predictable effect. Know the present perfectly, and you know the future. This was the gospel of classical physics. This was what made science powerful and authoritative. And Poincaré was saying it was wrong. Not wrong in detail, but wrong in principle. The universe wasn't a clock. It was something stranger, something that obeyed laws but remained unpredictable. That was heresy. So, it was buried in academic journals and forgotten for decades, until computers powerful enough to actually calculate three body trajectories revealed that Poincaré was right all along. The universe had been trying to tell us something profound, and we refused to listen because we didn't like what it was saying. Now, here enters Richard Feynman. In the 1960s, Feynman was working with computers to simulate physical systems. He programmed a computer to calculate the orbit of three gravitationally interacting bodies. He started with very precise initial conditions. The computer calculated future positions using Newton's laws, step by step. Everything seemed to work. Then Feynman did something interesting. He ran the simulation again, but changed the initial condition of one of the bodies by just 1/1,000,000th of a centimeter. An absurdly small change. At first, the two simulations were practically identical. The orbits looked the same, but after a few orbits, small differences started to appear. And then, suddenly, the orbits became completely different. In one simulation, one of the bodies was ejected from the system. In the other, all three remained bound. Feynman was fascinated and disturbed. He realized this wasn't a numerical problem or round-off error. It was the real behavior of the system. And he started explaining this in his lectures with an analogy that became famous. Imagine you're playing pool on a perfectly smooth table, with perfectly spherical balls, without friction. You hit the cue ball and it strikes other balls. If you want to predict where the cue ball will be after 10 collisions, you need to know the initial position and velocity with absurd precision. And if you want to predict after 50 collisions, you need to account for the gravitational attraction of people around the table. And if you want to predict after 100 collisions, you need to account for the gravitational attraction of the stars, because each tiny influence, however small, eventually dominates the system's behavior. This is chaos, and this is not a failure of our ability to measure or calculate. It's a fundamental property of nonlinear systems with 3 or more degrees of freedom. The universe is built this way, not by accident. not as a limitation we might overcome with better technology, but as a deep mathematical fact about how reality works. And Feynman wanted everyone to understand this because it meant that the dream of perfect prediction was dead, and we needed to stop pretending otherwise. Feynman explained that there are two types of systems in nature. Simple systems, like a pendulum or two orbiting planets, are predictable. Small errors in initial conditions lead to small errors in prediction. If you're off by 1% in measuring the starting point, you'll be off by roughly 1% in your prediction. Linear systems, well-behaved systems, the kind of systems Newton thought the entire universe was made of. But chaotic systems, like three orbiting bodies or Earth's climate, exponentially amplify small errors. This amplification is characterized by something called the Lyapunov exponent. If the Lyapunov exponent is positive, the system is chaotic. This means the distance between two trajectories that start very close grows exponentially with time. Mathematically, if the initial distance is delta zero, after time, the distance is approximately delta zero times e to the power of lambda t, where lambda is the Lyapunov exponent. For the three-body problem, lambda is typically positive. This means if you have a 1 millimeter uncertainty in initial conditions, after 1 Lyapunov time, the uncertainty becomes 1 centimeter. After another Lyapunov time, it becomes 1 meter. And so on, until prediction becomes completely useless. For the solar system, the Lyapunov time is approximately 5 million years. This means we can predict planetary orbits for a few million years, but beyond that, impossible. Even knowing all the laws of physics and having super-precise measurements of current positions. The chaos inherent in the gravitational dance of planets means that tiny perturbations, tiny gravitational tugs from asteroids, tiny variations in solar radiation pressure, all of these accumulate and eventually dominate the long-term behavior. Our solar system's configuration 500 million years from now is fundamentally unknowable. Not because we haven't tried hard enough, but because the universe forbids that knowledge. The disturbing lesson that Feynman wanted us to understand is not that math is hard, it's that the universe has intrinsic limits of predictability. He used to say, nature doesn't care what we want. It doesn't care if we want to predict the future. It simply is, and part of what it is chaotic. Feynman went further. He argued that most interesting systems in nature are chaotic. The motion of three stars, yes, but also climate, turbulence in fluids, heartbeat patterns, population dynamics, the stock market. All these systems have sensitivity to initial conditions. All amplify small perturbations. And this means the idea of a perfectly predictable universe, a universe where a supercomputer could calculate the entire future, is fundamentally wrong. It doesn't matter how powerful the computer is. It doesn't matter how precise the measurements are. Chaos is a fundamental barrier, not a technological barrier, not a temporary limitation, a permanent feature of reality. And here's the really disturbing part. Chaos is deterministic. The equations governing three orbiting bodies are perfectly deterministic. There's no randomness in them. Given an exact initial condition, there exists only one possible future. But in practice, we never have exact initial conditions. There's always measurement uncertainty. There's always noise. And sensitivity to those conditions makes the future effectively random, even though it's deterministic in principle. This is what philosophers call deterministic chaos, and it dissolves the distinction between order and disorder, between predictability and randomness, between natural law and chance. The universe is lawful but unpredictable. It follows rules but surprises us. And that paradox sits at the heart of everything we experience. Feynman liked to explore a paradox. If the universe is deterministic but unpredictable, what does that mean for free will? If your actions are determined by the laws of physics and the state of the universe now, you don't have free will. But if the future is unpredictable due to chaos, then in what sense is it determined? Feynman didn't have a definitive answer, but he argued that the distinction between determinism and randomness becomes meaningless in chaotic systems. For all practical purposes, the behavior is random, even though it's generated by deterministic laws. This idea became known as deterministic chaos, and it's deeply disturbing because it dissolves the distinction between order and chaos, between predictability and randomness, between natural law and luck. You can't say the universe is purely deterministic, because determinism without predictability is hollow. You can't say it's random, because it follows precise mathematical laws. It's something in between, something our language doesn't have a good word for. Feynman called it the edge between knowing and not knowing, and he thought that's where the most interesting physics happens. That's where complexity emerges. That's where life becomes possible. Because if everything were perfectly predictable, nothing new could ever happen. And if everything were purely random, no structure could ever form. Chaos sits in that sweet spot, that narrow zone where lawfulness permits unpredictability and unpredictability permits novelty. And understanding this changes everything about how you think about cause and effect, about science and knowledge, about what it means to understand the universe at all. In 1963, Edward Lorenz discovered atmospheric chaos while simulating climate models. He realized that small changes in initial conditions led to completely different predictions. This became known as the butterfly effect. A butterfly flapping its wings in Brazil could, in principle, cause a tornado in Texas. Not because the butterfly is powerful, but because the atmosphere is a chaotic system that amplifies small perturbations. The butterfly doesn't cause the tornado in any normal sense, but its tiny influence, combined with millions of other tiny influences, gets amplified through the nonlinear dynamics of atmospheric fluid flow until it affects large-scale weather patterns. This means weather prediction has a fundamental horizon. Currently, we can make useful predictions for about 7 to 10 days. Beyond that, predictions become no better than random guessing. Not because our models are bad, not because we don't have enough data, but because the atmosphere is chaotic, and small uncertainties grow exponentially. Feynman saw Lorenz's work and immediately recognized the connection with the three-body problem. Both are examples of nonlinear systems with sensitivity to initial conditions, and both show there are fundamental limits to scientific prediction. You can understand the laws perfectly and still not be able to predict the outcome. This was revolutionary. This overturned centuries of scientific philosophy. And most people still haven't fully absorbed what it means. We still act as if more data and better computers will eventually let us predict everything. But Feynman knew better. He knew chaos is a wall we can't climb over, no matter how hard we try. And he thought accepting that limitation was liberating, not depressing, because it meant the universe would always have the capacity to surprise us. But here's where Feynman really differentiated his perspective. Most physicists saw chaos as a problem, an embarrassing limitation. Feynman saw chaos as a profound discovery about the nature of reality. He argued that chaos is what makes the universe interesting. If everything were perfectly predictable, the universe would be boring. There would be no surprises, no creativity, no evolution or innovation. Chaos allows small fluctuations to amplify and create novelty. It allows simple systems to produce complex behaviors. It allows order to emerge spontaneously in certain regimes. Feynman saw beauty in chaos, not frustration. He said, the goal of physics is not to predict everything, it's to understand the fundamental laws. And one of the fundamental laws is that systems with three or more strongly coupled degrees of freedom tend to be chaotic. That's a law of nature as much as conservation of energy. And it tells us something deep. The universe is not a clock. It's more like a kaleidoscope, where small rotations create completely new patterns. Every configuration is lawful, but the sequence of configurations is unpredictable. And that's not a failure of the universe. That's how it expresses its creative potential. Chaos is the engine of complexity, the source of everything interesting that happens. Without chaos, you'd have perfect crystals extending infinitely in space. With chaos, you get galaxies and planets, and life, and consciousness. Feynman believed chaos was a gift, not a curse, and we should stop mourning the death of perfect predictability and start appreciating the universe we actually inhabit, which is far more fascinating than the clockwork universe Newton imagined. Let's talk about the practical implications of this. The three-body problem isn't just an abstract mathematical exercise, it appears everywhere in astrophysics. When you have a binary star system with a planet orbiting, that's a three-body problem. When you have the Sun, Jupiter, and an asteroid, that's a three-body problem. When you want to plan space missions that use gravitational assists from multiple planets, you're dealing with three-body problems. And in all these cases, the chaotic nature of the problem means you can't make long-term predictions with certainty. You can calculate probable trajectories. You can use statistics. But absolute certainty? Never. NASA discovered this the hard way when planning missions to Jupiter and Saturn. They had to constantly recalculate trajectories because small measurement errors or small perturbations from minor bodies accumulated over time. Even with our best instruments and most powerful computers, we can't predict spacecraft positions years in advance with perfect accuracy. We have to continuously update our models with new measurements. The chaos inherent in multibody gravitational dynamics makes that necessary. In stellar systems with multiple stars, chaos reigns absolute. Three-star systems are extremely unstable in most configurations. Frequently, one of the stars is ejected, transforming the triple system into a binary system. This happens because orbits are chaotic, and eventually one of the stars gains enough energy in a close pass to escape. Astronomical observations confirm this. Triple systems are rare and usually young. Older systems tend to be binary or solitary because triple systems destabilized over time. Chaos isn't just theoretical. It shapes the actual structure of the universe we observe. It determines which configurations are stable and which fall apart. And it means that the universe we see today is just one possibility out of many that could have existed with slightly different initial conditions. And there's more. The three-body problem helped understand planetary formation. When a protoplanetary disk collapses to form planets, you have millions of small bodies interacting gravitationally. It's an n-body problem, which is even worse than the three-body problem. The dynamics are completely chaotic. Small planetesimals collide, merge, or are ejected from the system. Computer simulations show that the final configuration of a planetary system depends critically on small details in the initial distribution of mass and angular momentum. This means planetary systems are unique. No two systems are identical. And it also means the formation of our own solar system had an element of luck. If initial conditions were slightly different, Earth might not exist, or it could be in a different orbit, or Jupiter could have been ejected. Chaos made our solar system possible, but also made it unpredictable. Every planetary system is a frozen accident, a particular outcome of chaotic dynamics that could easily have been different. Look at the asteroid belt. There are gaps called Kirkwood gaps, where almost no asteroids exist. These gaps correspond to orbital resonances with Jupiter. An asteroid in these orbits enters resonance with Jupiter, and the resulting chaotic dynamics eventually ejects the asteroid from the belt. This is a direct effect of the three-body problem: Sun, Jupiter, asteroid. The resonance makes the orbit chaotic, and the asteroid is expelled. This process clears certain regions of the asteroid belt over millions of years. We can see chaos at work, sculpting the architecture of the solar system, determining where matter can stably exist and where it cannot. The distribution of asteroids we observe today is a map of chaos, showing us which orbits survived and which were destroyed by the unpredictable dance of gravitational interactions. Feynman also explored the philosophical implications. If the universe is chaotic, what happens to causality? Normally, we think causes lead to effects. If you know the cause, you can predict the effect. But in chaotic systems, minuscule causes can have gigantic effects. A quantum fluctuation microscopic in scale could, in principle, be amplified by a chaotic system until it affects macroscopic events. This blurs the line between the quantum world, where uncertainty is fundamental, and the classical world, where we think everything is determined. Feynman speculated that chaos could be the bridge between quantum mechanics and classical mechanics. In quantum mechanics, we cannot know position and momentum simultaneously with infinite precision due to Heisenberg's uncertainty principle. This fundamental uncertainty is on the order of h bar, Planck's constant divided by 2pi. In non-chaotic systems, this microscopic uncertainty remains microscopic, but in chaotic systems, it can be amplified to macroscopic scales. This means the classical world inherits fundamental unpredictability from quantum mechanics through chaos. It's not just that we don't know how to measure well enough, it's that the universe doesn't permit infinitely precise measurements, and chaos makes that limitation relevant for large-scale phenomena. Quantum mechanics says you can't know everything about a particle. Chaos says that ignorance matters even for planets and stars. Together, they tell us the universe is irreducibly uncertain, from the smallest scales to the largest, and that uncertainty isn't a temporary condition we'll overcome with better technology. It's woven into the fabric of reality itself, and we need to build our worldview around that fact instead of pretending it doesn't exist. Think about this for a moment. Earth's climate is chaotic. Weather forecasts are reliable for a few days, maybe a week. Beyond that, they become useless. Why? Because the atmosphere is a turbulent fluid governed by nonlinear equations. Small fluctuations are amplified, and these small fluctuations include quantum effects in molecular motions. So tomorrow's weather is, ultimately, influenced by today's quantum fluctuations, the macroscopic connected to the microscopic through chaos. This is profound. It means we cannot completely separate the quantum world from the classical world. And it means unpredictability is not just ignorance. It's ontological. It's in the structure of reality. You could have perfect knowledge of classical physics and still not be able to predict climate decades in advance, because quantum uncertainty feeds into atmospheric chaos and gets amplified until it affects whether it rains in London next July. Feynman loved this idea because it broke the arrogance of deterministic science. It said, "You will never know everything. You will never predict everything. And it's not because you're incompetent. It's because nature is like this." And he saw that as liberating. You don't need to worry about building the definitive supercomputer that predicts the future. It won't work. Instead, you can focus on understanding principles, appreciating the beauty of natural laws, and accepting that the universe will always surprise you. The goal of science isn't control, it's understanding. And understanding includes accepting what we cannot know. That was Feynman's message, and it's more relevant today than ever, as we build ever more powerful AI systems and claim we're on the verge of predicting everything. we're not. Chaos guarantees we're not. And pretending otherwise is not just wrong, it's dangerous, because it makes us overconfident in predictions that are fundamentally unreliable. Before we continue, if you're enjoying this content, hit that like button now. It helps more people discover these disturbing ideas that Feynman tried to teach us. And subscribe to the channel so you don't miss the next videos, where we'll dive even deeper into the paradoxes of physics. Now, let's connect all of this with other discoveries. The three-body problem doesn't exist in isolation. It's part of a larger revolution in 20th century physics and mathematics. The discovery that complexity can emerge from simple rules. Before Poincaré and chaos, scientists assumed simple systems had simple behaviors, and complex systems needed many parts or complicated rules. But chaos showed that three bodies following one simple rule, Newton's law of gravitation, can produce arbitrarily complex behaviors. This opened the door to chaos theory, fractals, complex systems, and the science of nonlinearity. It revealed that the universe is fundamentally richer than we thought. That simplicity in laws doesn't imply simplicity in outcomes. That determinism doesn't imply predictability. These distinctions are crucial, and most people still confuse them. Mitchell Feigenbaum discovered in the 1970s that there is a universal root to chaos. Completely different systems, from fluids to insect populations, follow the same mathematical pattern as they become chaotic. This universality suggests chaos is not accidental. It's a deep structure of mathematics that appears in many physical contexts. Feynman was fascinated by this. He saw chaos as another layer of order in the universe, a higher-level order that governs the transition from predictability to unpredictability. There are laws about how systems become lawless. There are patterns in how order breaks down. This metastructure, this order behind chaos, suggested to Feynman that the universe was even more deeply mathematical than Newton had dreamed. But the mathematics involved nonlinearity, feedback, sensitivity, all concepts foreign to classical physics. Understanding these required a new kind of thinking, a new mathematical language, and Feynman was one of the pioneers in developing that language through his work on path integrals and quantum mechanics, which also dealt with inherent unpredictability. And there are more connections. The three-body problem helped understand galaxy formation. When galaxies collide, their stars don't collide directly, but interact gravitationally. You have billions of three-body problems happening simultaneously. The dynamics are chaotic and result in complex structures like tidal tails, bridges between galaxies, and eventually, merger. Modern computer simulations show that the final shape of a merged galaxy depends critically on the initial conditions of the collision. Impact angle, relative velocities, mass distribution, everything matters. And because the dynamics are chaotic, small differences produce very different results. This explains why elliptical galaxies, which form from mergers, have such varied shapes. Each merger is unique, shaped by chaos. No two galaxy collisions produce the same result, even if the galaxies are similar, because tiny differences in initial conditions amplify through chaotic dynamics until they determine the large-scale structure. When you look at the night sky and see elliptical galaxies, you're seeing frozen chaos, the end result of gravitational interactions so complex and sensitive that they could never have been predicted in advance. The universe we observe is one possibility among countless others, and chaos is what makes each outcome unique. Every galaxy is a work of art painted by chaos on the canvas of space-time, following strict laws but producing endlessly varied results. And this is true not just for galaxies, but for everything. Solar systems, planetary atmospheres, ocean currents, ecosystems, all of them products of chaotic dynamics operating under simple laws. Complexity emerges not despite simplicity, but because of it. Because non-linear interactions in simple systems naturally produce chaos, and chaos naturally produces structure and pattern through self-organization. The disturbing truth Feynman wanted us to face is this: we live in a universe that is lawful but unpredictable, deterministic but uncertain, simple in principle but complex in practice. And that combination is not a temporary state we'll overcome with better science. It's permanent. It's fundamental. It's who we are and where we live. The three-body problem is not just a mathematical curiosity. It's a window into the soul of the universe, revealing that reality operates on principles that defy our intuitions and frustrate our desire for control. But Feynman believed facing this truth was better than living in comfortable illusions. Better to know the universe is chaotic than to pretend it's a clock we could wind up if only we were smart enough. Better to accept our limitations than to chase impossible dreams of perfect prediction. Because once you accept chaos, once you truly understand it, you can work with it instead of against it. You can build robust systems that survive unpredictability. You can make probabilistic forecasts instead of false certainties. You can appreciate the beauty of a universe that constantly creates novelty instead of mechanically grinding through predetermined patterns. This was Feynman's gift to us: the recognition that chaos is not our enemy. It's the condition of our existence, the source of everything interesting, the reason the universe is worth studying at all. Without chaos, physics would be trivial. With chaos, it's an endless adventure into the unknown. And that's exactly how Feynman thought it should be. He lived for discovery, for surprise, for the moment when nature reveals something completely unexpected. And chaos guarantees those moments will keep coming, forever, because we can never exhaust the universe's capacity to surprise us. That's not a limitation. That's a promise. The universe will never become boring. We will never solve everything. There will always be mysteries because chaos continually generates new patterns and phenomena from old laws. And that means science will never end, understanding will never be complete, and wonder will never die. That's the message of the three-body problem, and that's why Feynman thought everyone should understand it. Not to become pessimistic about science's limitations, but to become realistic about its scope and excited about its endless possibilities. We don't need perfect prediction. We need deep understanding. And chaos, properly understood, gives us that. It shows us why the universe is the way it is, why complexity exists, why novelty emerges, why the future is open. These are answers, not failures. They're gifts from nature, telling us what kind of universe we actually inhabit. And it's a far more interesting universe than the clockwork mechanism Newton imagined, precisely because it's chaotic, unpredictable, and alive with possibility.